In this show, we find out something concrete about cement. We also see the people who snap to attention when you plug in an appliance. First, David's going to appeal with some video salesman.
This is a video monitor. This is a TV set. And this is both. Now that we've cleared that up, the confusion created by connecting video and computer technology may well never clear up. The best we can do is to try to keep up with it all. In the early days, a monitor used to be a critical display device that cost $10,000 and told you much about the picture it displayed. Nowadays, monitor means a stripped-down TV set that shows a theoretically better picture than a full-fledged TV set. If you're shopping for an IBM-compatible computer monitor, good luck. For that, you're going to need a knowledgeable computer salesman or a reliable fortune teller. You've got about a 50% chance of success with either. For the purposes of this item, computer monitors don't exist. The theoretical benefits of a monitor are many. The practical benefits are few. Consider this. A radio is actually two things in one box, a radio receiver and a speaker. A TV set is a radio set with pictures. A pair of radio receivers tunes to radio transmissions that carry the sound and its associated picture, the audio and the video. A speaker and a cathode ray tube present the received signals to you. Now, since TV sets exist in the millions, it behooves your average home video device to be able to connect to them. It does this with an internal RF unit. The RF stands for radio frequency. The RF unit is indeed a small, low-powered TV transmitter operating on channel 3 or 4, depending on your preference. Now, sometimes when I say this, people get mad at me. There can't possibly be a little transmitter in a VCR. Okay, here goes. This is probably highly illegal, but we're just going to do it in the name of science. There. This VCR now has an ordinary pair of rabbit ears connected to its out socket. There, the TV set's receiving the signal right through the air. Gee, our own little TV station. But don't try this at home. The guys in suits will come knocking on your door. Ordinarily, you connect the output of the VCR directly to the antenna terminals of the TV, and nothing broadcasts out of the shielded cable. Using the video and audio connectors between the VCR and a so-called monitor eliminates a lot of processing. It eliminates the process of modulating the transmitter and receiving and demodulating the picture and sound. Now, there are people that will tell you that the quality's better if you're using the video and audio connections, but those are people who've never looked at the picture in either mode. With a professional tape machine and a proper monitor, the quality of the video is noticeably better. But the playback quality of any modern home VCR is so lousy that the RF connection scarcely makes a difference. RF connections do require that the TV set's properly fine-tuned, but most of them do that automatically. The real drawbacks of the RF connection come as confusion. When you have a couple or a few video devices to connect together, is that channel 3 or is that the VCR? Most modern TV sets come with 1, 2, or 3 sets of video and audio connectors, and using these to switch among various devices can save some confusion. It can save some confusion. Usually it doesn't. Whatever set of connections you choose to use, there's a lot of bullpucky about what to make the connections with. If you don't remember anything else about video, remember this. In all of the television studios in all of North America, there is not one single gold-plated video connector. You just save some money. It's ironic, but because video is a complicated wideband signal, the interconnection standards that were chosen for it make it very tough to hurt. Over a distance of 100 feet or more, the proper cable's a must. Over the distance of a few feet, well, a little demo. The picture that you're watching right now is coming through all of these alligator clips and 10 feet of lamp cord. Unless your reception is pretty bad to start with, you'll notice that the picture is fine. Here, I'll just prove it. I'll disconnect the shield. This one's the video. Now, I'm not recommending that you use lamp cord for your connections. Shielded cable is best. Just don't spend a lot on cables. The shield is important for interference reasons, but the characteristics of the cable only come into play on long runs. This bundle of tinfoil and wax paper is officially a capacitor. 2 sheets of aluminum foil are rolled up with the wax paper electrically separating them. If I connect this across the video feed to this monitor, the picture smears. Officially, the high-frequency details are getting soaked up in the capacitor. This is electrically the same as a treble control. Long coaxial shielded cables behave just like this capacitor I smeared the video with. Credier cable has more capacitance, but over a short distance, you'll never notice it. So the next time some know-it-all poo-poos your cheap cables, you know what to tell them. Maybe you can have all your gold-plated cables melted down into jewelry.
It says push here, but it still does not work. How come? I am pushing, pushing, pushing.
Tomorrow morning, while you're staring at your coffee pot in a stupor, reflect on the following fact. The electricity that you're using can't be stored or manufactured in advance. Someone is at the other end of this appliance plug. Here they are now. This is the System Control Center of Ontario Hydro. From the array of chart recorders and gauges, the electrical ebb and flow of society can be observed. Your toaster represents a load of a little over 1,000 watts. At the turn of the century, communities operated their own electrical generation equipment. When Uncle Clem made his morning toast, George down at the generator knew about it. The interconnection of many generators and the loads that they serve helps to smooth out the demand and supply of electricity. Ontario Hydro has over 300 generators and 3 dozen generating stations located around the province. Most of the generators operate on falling water from rivers and streams, hence the name hydro. Some operate on steam from nuclear reactors, and the remainder burn fossil fuels to create steam for the machines. This is a chart recording for a typical day in Ontario. The chart is a little hard to read at first. The chart pen moves to the right to indicate increased demand, and the width of the paper represents 1,000 million watts, 1,000 megawatts. To avoid having a 4-foot wide piece of paper, when the pen reaches the right-hand side, it snaps back to the left and starts over. So you have to add 1,000 megawatts to the amount every time this happens. Before our very eyes, the demand dropped almost 100 million watts. A glance at the clock showed why. It was lunchtime in Ontario, and the machines of industry were being shut down for a sandwich break. Some generators will have to be shut down for lunch too. This is a station in northern Ontario winding down. Putting generators on and offline is done with a phone call to stations all over the province on a minute-to-minute basis. If you'd like to try this job out, here are a few of the facts you need to know. The hydroelectric stations can be turned on and off quickly. It's almost as simple as turning a water valve on and off. But a lot of the hydros rely on water stored in reservoirs during the springtime, so you can't consider them an endless solution to all of your problems. Controlling hydroelectric generators means adjusting the water levels on rivers and lakes, so you have to consider the impact on the communities around the stations. The nuclear stations take a day or more to start up, so you have to be reluctant to shut them down. They're mostly used to supply the constant base load, as the straight line on their charts indicates. The fossil fuel plants take a few hours to get up to speed, but Burning coal, oil, or natural gas to generate electricity is the most expensive and unpopular method at your disposal. The coal plants are the most logical choice to operate during daily peak periods. Watch it though, the coal comes in by boat, and this is Ontario, so you can't get more during the winter freeze. These wires bind together all of the communities and generators. Like the wiring in your house, they have a rated capacity and are protected by circuit breakers. It's hard to believe, but electricity seeks its own path in all of this wiring. If every community generated just enough for its own needs, no current would flow in the interconnections. As one area undergenerates, current flows in from all directions. In the case of overgeneration, current flows out. Monitoring the amount and direction of current flow is important. If a circuit breaker trips on one transmission line, current will take another route, possibly overloading something else. So you can't just turn stations on and off willy-nilly.
And as people get up in the morning, the load starts to trickle in.
Some of the electrical demands are predictable. Almost everyone sets their alarm for 7 a.m., gets up and turns on the coffee pot and some lights. Demand increases as industry comes on stream. Then there's lunch. At sundown, everyone turns on the lights, and street lighting comes on automatically. The weather plays an important role too, in the use of air conditioners, heaters, and even the decision whether or not to cook a roast in the electric oven.
For the other people on the other side.
It's okay if your mind's a little boggled at this point in the story, but there are more boggling thoughts to be had in this room. We've been looking at the province of Ontario, but Ontario is connected to all the other states and provinces, from the north to the south and as far west as the Rocky Mountains. The interconnections are formed by tie lines to neighboring electric companies. Monitoring current direction and amount tells who is over or under generating. It's interesting to note that you still can't tell which electricity is which, just who is under or over generating. The day we visited, Ontario was buying power from Manitoba. This is done by prior arrangement. New York and Ontario were in balance here. No current flow. The interconnection of companies helps in two ways. On a minute-to-minute basis, sundown comes at different times in different places, and on a long-term basis, the air conditioning load in the summer against the heating load in the winter. Our North American power is 60-cycle alternating current. The 60-cycle alternation is a direct result of the exact RPM of the generators supplying the power. If at some moment all of the electric companies are over-generating, the frequency will rise a small fraction all over the east half of the continent as the generators speed up a bit, maybe to 60.02 cycles per second. The reverse is true in the case of under-generating. Since electric clocks rely on a perfect 60 cycle per second frequency to keep time, the electric companies compare an ordinary electric clock to a fancy one tied to a common time standard. If the electric clock loses or gains a little time, the companies will all over or under-generate to adjust it, usually in the dead of night. Who would have ever thought that making toast was so interesting? Next on Acme, concrete or cement. One way to start a piece like this would be to show you a whole bunch of buildings, sidewalks, and bridges. Then we could make some point about concrete or cement, making it all possible. In the last 100 years, some pretty incredible structures have been built from cement or concrete. Okay, cement is not concrete. Concrete is comprised of sand, little stones, and bigger stones. Sand and little and big stones have strength and are cheap. On their own, though, it's difficult to build anything with that mix. Cement is a glue that's used to hold together the sand and the rocks. Sand, rocks, and cement is known as concrete. The idea goes way back in history. The first cement was probably just clay, but modern cement seems to have had its birth within the last 250 years in England. The cement that surrounds us since then is almost all Portland cement, named because of its similarity to Portland stone. Portland cement is a fine powder that will harden permanently when mixed with water. The reason that we didn't show you a bunch of incredible structures at the start of this item is that cement itself comes from a more incredible place. This is St. Lawrence cement in Mississauga, Ontario. Portland cement is made from things that come out of the ground. Their exact chemical composition is important, but it boils down to limestone and clay. These basic sounding substances have interesting chemical structures formed over millions of years. The process of making Portland cement will reverse some of this chemical history. Even though making cement looks like making mud cakes, the ingredients are mixed with almost pharmaceutical attention to proportion. This aerofall mill is 3 stories high and contains 120,000 pounds of 4-inch steel balls that pulverize its contents into a fine powder. It's run by a 3,000 horsepower motor. The pulverized stone is drawn up into these cyclonic classifiers. Here, fine powder is separated or classified from the coarser product. The coarse goes back to another mill for another beating. The fine begins a trip to one of 2 places. The next step in creating Portland cement is to burn the ingredients, but there are 2 main methods. The wet method ensures the most thorough mixing. The powders get further ground with water in a slurry mill. The liquid slurry travels to one end of a large rotating kiln. Oh, did I say large? I meant huge. The kiln is longer than a football field and 12 feet in diameter. As the slurry moves through the rotating kiln, several changes occur. In the first section, the slurry is dehydrated at about 260 degrees Celsius. In the center of the long tube, the material is calcinated at 875 degrees Celsius. Calcining is the process of converting a metal into its oxide. The metal in question is the calcium in the limestone. The hot end of the rotating tube is heated to 1,540 degrees Celsius. Here the material burns, creating hard little balls of cement called clinker. The kiln is fired with powdered coal. The unburned residue from the coal will become part of the final chemical makeup of the cement. The final step in the kiln process is a rapid cooling. The chains serve as a curtain that prevents flying bits of clinker from being projected back in the wrong direction. The sparks are hot clumps breaking up. Cooling is courtesy of 11 200 horsepower fans. The rapid cooling locks the chemical changes in place. Even though the dry process of making cement is more efficient, it's a little trickier. The primary difference is that calcination is done in a separate heater before the mix enters the kiln. The material is preheated in this tower before it enters the kiln. Like most continuous industrial kilns, the wet and dry kilns have to operate 24 hours a day, 7 days a week. In this plant, a lot of thought has gone into the use of heat from one process by another. Exhaust gases from some processes are used as preheaters for other processes. As well, an elaborate system of dust control is de rigueur at a cement plant. This is a bag house, sort of like the interior of a giant vacuum cleaner. Each mill has one. The output of both wet and dry kilns are little hard beads called clinker. Clinker is basically cement, but it needs to be powdered. Well, powdered hardly does this unit justice. This is the cement mill. It takes clinker from the kilns and pulverizes it. It's not running right now because it uses 6.5 million watts of electricity. Clinker will keep on the shelf for a while, and the utility rates are better at night. There's a small one operating in the background of this shot. Most Portland cement from this plant is shipped in bulk. Only about 10% is bagged. Once activated by water, Portland cement will harden permanently. Portland will even harden underwater, although there are specific varieties for that if you're going to do that. Other flavors of Portland can be concocted to cure in huge lumps, say, like the Hoover Dam. When Portland cement is added to sand and rocks, it becomes concrete. And as long as there are no impurities in the filler, the hardened concrete will be as strong as stone. The St. Lawrence cement plant is capable of producing 125,000 tons per month. The large scale of operations is one of the reasons that cement can still be sold for just a few cents a pound. Too bad it doesn't taste good in coffee.